Okay, hello Precalc C. We're going to go over the rest of page 4 of the inequalities packet. We did basically all of this, well, we did the entire left column of the page together, so there's really just 2 problems left to do, but both of those problems are tricky. Here we go. 1 over x is, so I want to solve this inequality. 1 over x is between -5 and 3. How are we going to do this? Well, okay, this is sort of seemingly very simple, innocent problem, but already I am quite perplexed as to what to do next, because, we talked in class about how it would be a bad idea to multiply by x, because that's unhelpful, but it's maybe even worse here, because I cannot tell if x is going to be positive or negative, and in fact I suspect that there are going to be some positive and some negative values. Maybe a good way to get some intuition on this is to just plug in some numbers. Well, if x is 10, say, then that should be a solution, because 1/10 is less than 3. So there are certainly some positive numbers which are solutions to this inequality, large ones like say 10. Could there be some negative numbers which are solutions? Well, okay, I don't know. That one maybe is somehow a little bit harder for me, but maybe, well, -1, say, okay, or maybe -2 is a good answer. If x is -2, let's see if I've done that right. Yeah, if x is -2, then it is true. Sorry, I should have mentioned that when x is 10, it's important that 1/10 is not only less than 3, but of course any positive number is going to be greater than -5. So when I plug in -2 for x, I get 1 over -2 is -1/2. Well, -1/2 is in between -5 and 3. Okay, so the point is that the solution set to this inequality is going to contain some positive numbers and some negative numbers. And so if I'm trying to solve the inequality, it would be probably bad to make any kind of assumption. Well, it would be definitely bad to make any assumptions about whether x is positive or negative. And therefore, I don't have access to the move that we pulled in class. The move we pulled in class was to note that whenever both numbers in an inequality are positive, then that you can perform this reciprocation, and you get that the sign kind of flips. So 2 is less than 3, but 1/2 is greater than 1/3. And that this works if both numbers are positive. And we also said, what about if both numbers are negative? Maybe we don't need a kind of separate rule for this in some ways, because you could always just multiply through by a negative and then apply this rule. So this to me is the real rule, but okay, we can also talk about this one. If they're both negative, then what? Well, also the sign flips when you perform reciprocation, because this becomes -1/3 is greater than -1/2, and that's just true. So those, though nice, are simply inapplicable here, because well, they're inapplicable. Because I don't know whether x is positive or negative, and I have sort of a mixture of positive and negative numbers. Okay, how should we do this problem then? I can think of 3 different ways to do this problem, all sort of at differing levels of how much care you want to put into this. One thing you might do is to get over this whole difficulty with positive and negative numbers by just right off the bat splitting this problem up into cases. So let's just take the case where x is negative and take the case where x is positive, and let's just settle those 2 separately. This seems like a great idea, because, well, now, what do I know? I know that 1 over x, I know I'm looking for, I suppose I should say, I'm looking for all the numbers such that 1 over x is between -5 and 3, all the positive number. Over here I'm explicitly looking for all the positive numbers, x, such that 1 over x is between -5 and 3. And over here I will be looking for all the negative numbers, such that 1 over x is between -5 and 3. And so I have two separate cases to work with here. Okay, but, and this is a little bit subtle maybe, or maybe this is kind of obvious, if I'm explicitly addressing positive x values, then it is irrelevant, or rather I gain no information by being told that 1 over x is bigger than negative 5. Of course 1 over x is bigger than negative 5, because x is positive, 1 over x is therefore positive, and every positive number is bigger than negative 5. So this is sort of silly, maybe not even worth mentioning. The only content of this statement is the statement that 1 over x is less than 3. And similarly over here, if I know that x is negative, then I know that 1 over x is negative. And if 1 over x is negative, then of course it's less than 3, because every negative number is less than 3. Therefore, the only real content is over here. And so I now have sort of boiled this down to two simple statements. And, well, what's the simple statement here? It says that 1 over x is less than 3. But now I'm back in the kind of warm embrace of all positive numbers. Since I know that 1 over x is positive, then with these two positive numbers, well, there's a bunch of things I could do, but one thing I could do is apply this reciprocation rule. And if I reciprocate, I get that x is bigger than a third. Flipping the sign. Okay, what about over here? Well, now I get negative 1/5 is bigger than x. And so, where am I right now? Well, I have to be a little bit careful in how I interpret what was going on. Recall, I sort of split this up into cases, and so this statement that x has to be bigger than a third. Well, actually, this statement requires no. Well, actually, neither of these statements require any sort of further comment. What is the solution to this inequality? Well, it's all positive numbers bigger than a third, and all negative numbers which are less than negative a fifth. And actually, that's just the answer. The answer is going to be, maybe it's nice to put this on a number line or something, just to kind of bring it back to the Algebra 1 sort of way of looking at things. So, you know, here's negative a fifth, here's a third or whatever, and what have we just determined? We've just determined that if you are a positive number bigger than a third, then you satisfy this original inequality. By the way, that makes total sense now, kind of when I look at it, right? Because sort of tiny positive numbers don't work here, right? Like if x is 1/10, then you get 10 is less than 3, which is false. But big numbers, like as we said at the beginning, like 10, give me 1/10 is less than 3, which is true. And here we learn that almost all negative numbers also satisfy this equation. What doesn't satisfy it, the only thing that doesn't satisfy it is really tiny negative numbers, say negative a tenth, because then 1 over negative a tenth is actually negative 10, and negative 5 is not less than negative 10. Okay, so using all sort of matters of common sense, I've checked and to confirm that all of my logic is sort of correct here, and this is just the answer to the problem. Final answer, everything from negative infinity to negative 1/5, union everything from 1/3 to infinity. Alright, I mentioned that there were sort of other ways to do this problem. One way to do it, which is actually significantly easier, is to just do the whole thing kind of graphically. So what we do is we just make a graph of the 1 over x function. So I'll try to do that here with a little bit of accuracy. And now, what am I really asking when I'm asking to solve this inequality? Well, I'm essentially being asked, okay, when is this function between negative 5 and 3? Alright, so well, when is this function equal to negative 5? So just kind of go over here on the y-axis and just consult this point with y-coordinate negative 5. Well, of course, I don't even need to do any algebra. It's just obvious that it's the input negative 1/5, which will produce output negative 5 on the graph of 1 over x. And what is the other thing I care about? I want to know when 1 over x is less than 3. So I go over here to 3, and I see that I have input 1/3, which produces output 3, of course, on the graph of 1 over x. And now, sort of, I just kind of look at my graph, and I say, okay, well, what are the x values which will produce y values which are in between -5 and 3? Well, all of these numbers will produce an output which is between -5 and 3, and all of these numbers will produce an output which is between -5 and 3. And therefore that's the answer, right? Everything from -infinity to -1/5, and everything from 1/3 to infinity. Okay, that's pretty thorough. So that was almost kind of now like a warm-up or something to problem 13, which again is tricky because sort of every shortcut you sort of think you can make, you know, you can't make it. Okay, so you really have to be kind of quite careful. So let's go. This will be one of our sort of hardest inequalities problems that we're going to try to solve. So all right, here we are. What is the problem? It's when is x minus 12 over x less than 4? Okay. Well, this is going to be hard because even though this entire expression in the middle is going to be positive because it's between 1 and 4, because I have some subtraction going on here, it is not obvious to me at all that x has to be positive. I can easily imagine, and in fact there will be some negative values of x which are solutions to this inequality. So I find myself in a similar position of being unable to do much kind of manipulation with x because almost everything with inequalities is sensitive to whether the number is positive or negative, and I really don't know whether x is positive or negative. The only thing I could sort of maybe do is I could get a common denominator, so maybe let's just do that right now. So that gives me x squared minus 12 over x is less than 4. But right now, though it might be tempting to multiply through by x, I really shouldn't do that because if x is positive, then I get a certain sort of consequence. But if x is negative, I get a different consequence. And actually, I hadn't considered doing this, but you might pursue solving the problem that way with cases. That would probably work. Sort of like how we did the previous problem. You know, settle it for all positive values of x, then settle it for all negative values. Okay, I won't pursue that method here. I think it's maybe simpler because we do have some experience dealing with solving inequalities when we don't know whether x is positive or negative. So let's lean on that experience. What we haven't done before in this class is deal with this sort of situation in which it's a compound inequality. So in other words, I guess what I'm trying to say is if you took away this less than 4 and you just gave me the problem 1 is less than x squared minus 12 over x, well, we know exactly how to do that problem, right? We just move everything over to one side, we get a common denominator, and we reason from there. Let's just let's choose to do it that way. In other words, let's think of this compound inequality as what it really is. After all, when people write A is less than B is less than C, really this is just kind of a shorthand for two statements, right? This is maybe it's called a compound inequality. What we're really sort of saying is that A is less than B, you know, and B is less than C. And so we sort of it's fundamentally a binary relation, less than is, and we sort of jam it together using this kind of convenient linear symbol representing sort of two inequalities at once. Well then, in this case, we should just decompose it. So okay, what am I trying to say? I'm trying to say that really this statement says this and this. And if we want to find the x's which make this original sentence true, then we need to find x's which make this true and this true. In other words, I can solve now each of these inequalities separately, which is something I know how to do, and then I can find the x's which satisfy both of them. Okay, so that's what I'm going to do right now. I will, so subtract 1. So we get x squared minus 12 over x minus 1 is positive. And I guess I'll kind of move, get a little bit more room here. Let's see. Sure. Yeah, I guess I'll just kind of go here. That should be enough space. So, what's the other thing that's supposed to be true? It's supposed to be true that x squared minus 12 over x minus 4 is negative. Okay, screaming baby in the background you might be able to hear. We're going to ignore that. Alright, let's just do this problem now. So we get a common denominator. So x squared minus 12 minus x over x has to be positive. And we're looking for x's that also satisfy x squared minus 12 minus 4x over x is negative. Okay. Wow, this just factors, right? This is, I think it factors nicely. This is x minus 4, x plus 3 over x. What else? X represent, And this is, I guess, x minus 6, x plus 2 over x is negative. So, looking good. So, okay, how do I solve this? Using the same old methods, which is we think of this rational expression as having a having kind of a cubic type sign behavior, and so we're going to have a change of sign at -3, a change of sign at 0, and a change of sign at 4. But it's going to behave kind of like a cubic, and so this will be negative, positive, negative, positive. And therefore, the solution to this inequality is going to be, well, when is it positive? Answer, everything from -3 to 0, union, everything from 4 to infinity. Okay, how do I solve this inequality? Well, once again I have a cubic with leading coefficient positive. So we're going to have a sign change at -2, a sign change at 0, and a sign change at 6. And once again, the sign distribution will be negative, positive, negative, positive. But now, note that I'm trying to figure out when this expression is negative. And so the solution to this inequality is everything from negative infinity to -2, union everything from 0 to 6. Alright, and so that's basically it. Now all I need to do is kind of take the intersection of these two sets, so to speak. I mean, that's exactly what we want to do. So you can do this kind of maybe in your head, or if you prefer to do it with a graph, then you can do that. So I'll just do it the graphical way. So I'll make sort of 3 number lines, you know, kind of side by side or something, and adding every important point to it. What are the important points? Well, -3, -2, 0, 4, and 6. This is maybe a little bit overkill. 0, 4, 6. Because maybe this is not that hard, but all right. Well, what's the first inequality over there? Or what's the first solution set? Everything from -3 to 0, so all of this, and everything from 4 to infinity. Cha 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 cha. And what's this one? This one is everything from negative infinity to -2. And everything from 0 to 6. And so if you just look and see when these overlap, after all, recall that we're looking for values of x which make them both true. So the only time these two inequalities are both true is between -3 and -2, and between 4 and 6. Okay, And indeed, that's the final answer to this problem. The final answer to this problem is everything from -3 to -2, and everything from 4 to 6. Okay, so that was pretty hard. Okay, did we have a kind of another option here? I think that we did. The other option is to sort of take seriously that we are in the middle of a unit, actually done with this unit, on graphing rational functions. And so perhaps what we should just do is graph the rational function x squared minus 12 over x, and then just kind of look at it. Okay, so let's just do that now. Feel free to kind of stop this video if you're done with this conversation, but if you want to watch on for a few more minutes, what I'm now going to do is I'm going to consider the function f of x equals x squared minus 12 over x, which, by the way, factors into root 12 is 2 root 3. So this is x minus 2 root 3 x plus 2 root 3 over x. Why am I doing that? Because if we're going to graph this, we should care about what the roots are, and we should care what the sign chart is for this function. And what is that sign chart? Well, it's cubic. It's going to change sign at -2 root 3, 0, and 2 root 3. And it's going to go, negative, positive, negative, positive. Okay, and, well, I guess I need to clear a bunch of space here, so I might as well just do it now. There's no sort of good way to do this, but maybe just like that, or something, to make some space. What else do I know about this function? Okay, it's undefined at 0. Well, and of course, let's not forget that the function just really is, or was to begin with, x minus 12 over x, which means that as x goes to infinity, 12 over x is going to 0, and so this function has a slant asymptote. Slant asymptote of y equals x, and that there is a vertical asymptote at x equals 0. Because the function becomes infinite there. So, is there anything else I need to know? I don't think so. Roots, boom, boom, boom. So, now we'll just make a little picture right here of this whole thing. Okay, let's do it. I gotta kind of draw a little bit small. Let's see, how much kind of space do I need? Like a bunch. So maybe I'll go, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and let's just go here. What do I have? Vertical asymptote x equals 0. Slant asymptote y equals x. Roots at 2 root 3. So that's like 3.5 basically, ish. 1, 2, 3.5. And 1, 2, 3.5. And let's see, is there anything else that I kind of care about? I don't think so. This function's just going to kind of go jump and then jump. Okay, but before I graph it, what was the whole point of being able to graph this? I wanted to graph this because I wanted to know, when is this function in between 1 and 4? So when is this function in between 1 and 4? I'm cheating by getting some nice points before I draw my graph. Well, notice that if you first try to set this function equal to 1, then that really amounts to solving this equation. And so if you just set this function equal to 1, you find that the points of intersection are at 4 and -3. Alright, so if I go to, maybe a new color is needed now, like blue. If I go to -3, what do I get as my answer? I get 1, right? -3, of course. -3, 1 is a point on this graph, as is 4. Okay, what did I just do? I essentially just kind of reused the algebra work I did over here to sort of set this function equal to 1. I mean, you could, I suppose you could do it all over again if you really wanted to, right? You're just solving the equation when does 1 equal x minus 12 over x? Well, you multiply through by x, you get x equals x squared minus 12. So that's x squared minus x minus 12 equals 0. And what do you find? You get x minus 4x plus 3. Okay, so maybe now you trust the process here that those are the times when it's 1. And then the other thing to do is to set x minus 12 over x equal to 4. And now then you get x squared minus 12 equals 4x, and so x squared minus 4x minus 12 equals 0, and so that becomes x minus 6x plus 2. I do this so fast because we essentially did it already. And so what does that tell me? It tells me that the times when this function equals 4 are up at 6 and negative 2. So I have a point negative 2, 4, and I have a point 6, 4. Cha-cha. And so, what does this graph look like? Well, using my rational functions graphing skills, I can say that there's a slant asymptote. I never cross this slant asymptote because my function's never equal to x, because there's always a little bit, it's always off by a little bit. There's a root at negative 2 root 3. There's a vertical asymptote at 0. My function is negative until negative 2 root 3, positive in between negative 2 root 3 and 0. Then my function is negative between 0 and 2 root 3s, and it's also kind of infinite near 0. And from 2 root 3 on, it's positive. And what did I know? I knew that it sort of went through those 2 points. And so now, reaching for my sort of last kind of color here, what is this? This is the line y equals 4. What is this? This is the line y equals 1. And I can now see at a glance, kind of graphically, this is in some sense easier because I didn't have to like solve any inequalities or anything. All I had to do was just sort of graph the function and then look at it. That on the one hand, my function x minus 12 over x will be between 1 and 4 from negative 3 to negative 2, which is exactly what we got, and also from 4 to 6. Okay, so I think this is kind of a nice demonstration of sort of 2 different ways of doing this, and there was even the third way that I mentioned that I won't pursue, which is splitting it up into the case of x being positive and x being negative. You can try that if you want. Okay, goodbye.